So, hello everyone, and welcome back to the Urban Computing Skills Lab. Last time, as you remember, we considered some basic concepts, rules, and operations with probabilities. And there's actually one more concept and a theorem about it worth additional consideration, a separate one. Those are conditional probability and Bayes' theorem. And the importance of those two come from the fact that they lay in the very foundation of Bayesian inference, which actually is an important part of data science and machine learning. So what is the conditional probability? Let's start from a simple example. Recall the statistics of the weather in New York City, and we'll find out that snowfall in New York City happens approximately 11 days a year. So if, say, we're considering a probability of the event of taking a random day from the calendar, and that it will be snowing on that day, and actually 4 of those 11 days happen to be in January, again, according to the multi-year statistics. So now if we consider a probability of the event of taking a random day from a calendar, and that it is going to be snowing on that day, then the probability of such an event will be 11 divided by 365, so we have 11 positive outcomes, snowfall, and 365 possible outcomes, taking a random day from the calendar. So this is the probability. And it's approximately 3%. Now, if you know that the day you've chosen happened to be in January, so if you know that it's January already, then conditional to this knowledge, the probability of having a snowy day is already going to be much higher, because in January you only have 31 days, and 4 of them you actually see snow outside. So the probability now is 4 divided by 31, which is somewhat above 13%. So it goes much higher once we know that the day we've chosen is in January. So that's the idea of the conditional probability. Probability of one event conditional to the other event happening. Another example, let's say we are rolling 2 dice, and one gives us x value, the other gives us y. And we are wondering what is the probability that the sum of those 2 values will be higher than 6. From a simple symmetric consideration, you can see that this probability is 50%, because you can just reverse the numbers on the dice, replace 1 by 6, 2 by 5, and so on. And then for each outcome giving you some higher than 6, you have one single corresponding outcome giving you some lower than 6. So basically, you'll just stay with 50% of the possible outcomes giving you higher than 6. However, if you already know that the first dice came up 1, then your probability of getting the sum higher than 6 is going to be much lower. Because if the first dice, if x is 1, then your only chance to get the sum higher than 6 is to get the second dice, y, coming out as 6. So this probability of having the sum higher than 6, conditional to having the first dice coming out as 1, is actually 1 divided by 6, because you have the only option for the second dice, 1 out of 6 possible options. So this is the difference between probability of the event and the conditional probability of this event once we know that another event happened. Of course, this difference only takes place if the events are dependent one upon another. If they're independent, then there's pretty much no difference. But we'll talk about that later on. Now let's try to visualize the conditional probability. So let's get back to our original setting when we visualize the complex event as the sample space of the elementary outcomes, and the event is some area in this sample space. So now, what would it take us to visualize the conditional probability then? Well, first of all, the conditional probability of event x happening if y happened assumes that y happened. If y happened, it means that we are actually left with only part of all the options around. Because if y happened, then we can only have those 5 elementary outcomes which lay inside the area encircled as y. So now this is our new sample space. So basically what the conditional probability does, it just narrows down our sample space, leaving us with only those elementary outcomes which happen to lay inside the area of y. So now this is our new sample space. And the probability of event x here in this new sample space is 3 outcomes that satisfy x out of 5 possible outcomes is going to be 60%. While the probability of x in the entire sample space, regardless of whether y happened or not, will probably be different. So now, with this setting, it's very easy to see that the following rule is true. So if we're wondering what is the probability of both events to happen at the same time, which is the relative size of this area in the entire sample space, this size is pretty much the relative size of the area y in the sample space, multiplied by the relative size of x inside y, because x and y should happen at the same time. So this is probability of y, and this is the probability of x inside y. And we multiply those relative sizes to get the relative size of this in this. Or, alternatively, you can also say that the probability of x and y to happen at the same time is the probability of y to happen multiplied by a probability of x to happen once we know that y happened. So this is the rule. Now let's revisit the idea of independent events. Remember that last time we called events independent if the probability of the intersection, so if the probability of those two events happening together, is the probability of the first event multiplied by the probability of the second event. Now, in the setting of conditional probabilities, it's actually quite obvious to say that the events are independent, x is independent on y, if the conditional probability of x on y is the same as probability of x. So basically it doesn't matter whether event y happened or not, the probability of x stays the same. This pretty much means independence between those two events. And now if we stick with this definition, what it means that from the previous rule, probability of the intersection of two events, probability of both events happening at the same time, which is conditional probability of x conditional on y multiplied by probability of x. In this new setting, if x is independent on y, this conditional probability is the same as probability of x. So what we end up with is, again, this first formula. So from the second definition, we have the first definition to follow. Now, we'll make some use of that later, but let's consider another rule. That's called the summation rule. So probability of y, of event y, happening is thought as the cumulative probability of event y happening together with event x happening, and event y happening together with event x not happening. Because x happening and not happening pretty much covers the entire space of the opportunities, and those two events are obviously mutually exclusive, so you can sum up their probabilities. And that's what gives you a probability of the event y. Now, if we apply here the previous rule, we get this type of formula. Probability of y equals to the sum of probability of x multiplied by conditional probability of y if x happened, plus probability of not x multiplied by conditional probability of y if X not happened. It might sound a little bit boring so far, but let's see. We'll actually see in a few minutes how it works in practice. Before going into examples, let me finally tell you what the Bayes theorem actually is. Because I introduced the Bayes theorem at the very beginning, but so far we haven't reached the point when we talk about this. Now, that's a good time for that. So, the rule about probability of two events happening together, which, again, as we remember, is probability of y multiplied by conditional probability of x if y happened, could be actually rephrased if we flip x and y so that this probability will now become probability of x multiplied by conditional probability of y if x happened. So now those two terms happen to be exactly the same. It's the probability of x and y happening together. Since they are the same, let's express this term, conditional probability of x on y, through all the others. And we can do it that way. We can do it that way, just putting the sign equal between those two terms, which, as we know, are equal. So this is the Bayes theorem. And that was the proof of the Bayes theorem so far. You see, the proof is pretty simple. What is the meaning of the theorem? It allows you to figure out what is the conditional probability of one event on the other event happening if we know the inverse conditional probability. So if we know the conditional probability of x on y, we can figure out conditional probability of y on x. And this kind of flip is quite important, because in many cases, you can get conditional probability of x on y from the conditions of your problem, but this probability of y on x is something you just do not observe, something you do not know. And Bayes' theorem gives you an elegant way of figuring it out. Now I think it's time for an example. So imagine you stay on the bus station and you have two buses coming. One is Peter Pan bus and the other one is Megabus. You don't know which one of them actually came to the gate, because from outside you only see the door of the gate, you don't see the bus itself. But what you do know is that in the Peter Pan bus, there were 30 men and 20 women, 50 passengers in total. And in the Megabus, there were 10 men and 20 women, 30 passengers in total. Now first, assume that you don't know which bus came, so for you it's 50% each, so 50% that is Peter Pan, 50% that is Megabus, and you're like waiting next to the door, and you're questioning yourself, what is the probability of seeing a lady coming out? What is this probability? Well, one way of thinking might be, okay, what is the total? We have the total of 80 passengers. I don't know which bus came, so I don't care. There are like 80 passengers in total. 40 of them are women and 40 of them are men. So it's 50%. Unfortunately, this type of conclusion will be wrong, because actually we do not draw people from both buses with equal probabilities, in fact. Because if one bus came, then you have 50 people to choose from. 30 of them are men, 20 are women. And that's our choice, if the first bus came. If the second bus came, then we choose among 30 people. And the probability of choosing each of those persons is 1 divided by 30. In the first case, it was 1 divided by 50. So the outcomes of having each specific person are not the elementary outcomes which have the same probability. So then our logic about like choosing one lady out of 40 doesn't work anymore. What will work is a summation rule. So if we want to see a probability of lady coming out, let me get to the whiteboard for that. So what we need to do, we need to consider two cases. What is this probability if the megabus came or if the Peter Pan bus came? So the probability of seeing a lady equals the probability of seeing a lady conditional to the fact that the bus was Peter Pan multiplied by probability of having this bus actually from Peter Pan. Plus, it is the probability of seeing a lady if the bus is actually a megabus multiplied by a probability of having a megabus. So by assumption that we do not know which bus came, those are 50%. Now, what are those probabilities? Probability of seeing a lady coming out of Peter Pan bus is actually 20 out of 50, because we have 50 passengers in total and 20 ladies out there. So that's going to be 20 divided by 50. And the probability of seeing a lady out of megabus is 20 out of 30. So those are our probabilities. Now let's transform this and let's actually calculate the result. So it's going to be 2 divided by 5 multiplied by 1 divided by 2 plus 2 divided by 3 multiplied by 1 divided by 2. So now we end up with, we get rid of 2's here, and we get 1 divided by 5 plus 1 divided by 3, bring it to the common denominator. It's going to be 3 plus 5, so 8/15. So it's actually slightly higher than 50%, slightly higher than our naive guess of what will actually happen. So that's the probability of seeing a lady coming out, if we don't know which bus came. But now let's ask sort of an inverse question. Assume that you actually see the lady, because you are standing next to the gate and you're observing what happens there. So you see the lady coming out. Now, what is your how it changes your belief about which bus actually came? So what is the conditional probability that it was Peter Pan, conditional to the fact that you saw a lady coming out? And what is the probability, conditional probability of having a megabus if you see a lady coming out? So what is the condition? What is the probability that it was a megabus? So how seeing a lady will alter your belief about, probabilistic belief about which bus actually came. For this purpose, let's employ Bayes' theorem. So we're wondering, what is the probability of having a megabus if the lady comes out? We don't know that. We don't have any data given to directly quantify this probability. But we can use Bayes' theorem to relate it with the probability of having a lady coming out of megabus multiplied by the probability of actually having a megabus and divided by a probability of seeing a lady coming out. The probability of seeing a lady coming out, we just quantified that. It was 8 divided by 15. Probability of lady coming out of megabus. Probability of lady coming out of megabus, as you remember, is 20 divided by 30. We have 30 people there and 20 ladies. So it's 20 divided by 30. Probability of megabus coming, so far we believe it's 50%. And that's sort of Bayesian thinking, because we do not have any observations of those buses, but we believe that it's equally probable that each of them actually come. So, and we divide it by a probability of seeing a lady, which is 8 divided by 15. So now this is our probability that megabus came. Conditional probability. Let's transform that. Let's get rid of zeros. Let's get rid of 2's here. So it's going to be 1 divided by 3 divided by 8 divided by 15. Again, let's get rid of 3 here. So now what we end up with is 5 divided by 8. So before we started with believing that the probability of a megabus coming is 50%, but now once we saw one lady coming out, our belief altered, and now we give 5 to 8 that megabus actually came. And that's pretty much the key to Bayesian inference. Each new observation alters your belief about the reality. And now once you process all the observations, you end up with a final estimate. We'll certainly have a separate lecture about Bayesian inferences. It's not part of the summer boot camp. We'll have it in the course of applied data science, and later we'll also be touching on that in machine learning class. But for now, I just want to leave you with this idea and with this example of the application of Bayes' theorem. But in the end, let me actually give you another example which might show you like a more sort of a real-world application of the Bayes' theorem. So for that purpose, we'll need to revisit the summation rule. So before, we just considered two cases, event X happening or not happening. Now, let's consider X as a random variable, and in this case, we have multiple outcomes. The random variable X can be equal to like 1, 2, 3, etc. It can be equal to one of a possible discrete set of outcomes. Let's denote those outcomes as K, and this way the probability of Y will become a sum over K of probability of X equals K multiplied by probability of Y in case X equals K. That's pretty similar to the previous setting, just we replace the random event by a discrete random variable for X. Now with that, let's consider the following example. Say we are taking a water quality test. So we know that the test is 99% accurate, meaning that if the water is actually polluted, it will give you the red flag in 99% of cases. In 1% of cases, it might miss the pollution, actually. So it's 99% accurate. Also, let's assume we know that there are 10% of false alarms, meaning that if the sample is actually good, the test might tell you that it's bad in 10% of cases. And also, let us know that approximately 1% of all the spots we test are polluted. So now, with this information, once you take the sample, take the test, and get a positive result, what is the chance that the spot is actually polluted? You might probably say it's 99% because it's 99% accurate. But actually, if you think, this accuracy tells you a slightly different story. It's not about the probability of having a spot polluted if the test is positive. It's a different type of conditional probability. It's a probability of having the test positive if the spot is polluted. So that's the flipped conditional probability. And we're wondering what is the other way around. So what we're trying to figure out is that what is the probability of having the spot polluted if the test came out to be positive. So again, here we can employ Bayes' theorem to figure that out. And the Bayes' theorem will will leave us with this. So probability of the spot to get polluted, to be polluted, if the test was positive, is the probability of test being positive if the spot was polluted, which we know to be 99%, multiplied by the probability of the spot to be polluted, which we assume to be 1% because we know that 1% of all the spots is polluted. It's our belief. And divided by a probability of having a positive test. This is something we do not know. So we don't know what is the probability of having a positive test because we don't have any observations. We just took one test. We don't know what are the odds of getting positive test. Now, this chance can be estimated. Yeah, this is just incorporates our existing information, and this is something we don't know. So now the probability of having a positive test can be actually obtained from the summation rule. So probability of having a positive test is the probability of having a positive test if the water is polluted, multiplied by a probability of having the water, sorry, it gets back, by a probability of having the water polluted, plus the probability of having a positive test if the water was not actually polluted, multiplied by a probability of having the water not polluted. This is the summation rule. And now here, we know pretty much everything. We know this because this is our accuracy. This is 99%. We know this. The spot is polluted. It's 1%. We know this. What is the probability of having positive test if spot is not polluted? That's the probability of false alarm, 10%. And we know this. Probability of having the spot not polluted is 99% because it's 1% to have it polluted. So now, that's what we have.